Hi, welcome back. So in this video, we are doing part 2 of Convergence and Divergence, this time talking about series. So for series, in order to determine if they converge or diverge, we're going to need to look at partial sums of the series. So this is one of the first things we're going to talk about. As a note, when we consider series, they could be either finite or infinite. They could have a finite number of terms being added or an infinite number of terms being added. And all finite series are going to converge because we just have a finite number of things we're adding together. There's going to be an end to it, so we could compute what that value is. And so instead, we're more interested in infinite series. We want to know, does an infinite series converge? When we add up all the things, does it somehow approach a value? Okay, so let's talk about these partial sums, and then we'll get into how we use them to talk about convergence and divergence. So if we are given an infinite series, the sum from n equals 1 to infinity of a sub n, this looks like a1 plus a2 plus a3, etc., forever and ever, then the nth partial sum of the series is the sum of the first n terms. So we use this as s sub n. I'm using a capital S, it's just what I'm choosing to use. And this is equal to the sum from I equals 1 to n, so we're only looking at a finite number of terms, of a sub I. So we take a sub 1 plus a sub 2, keep adding until we get to a sub n. So instead of adding in infinite terms, we're just looking at the first n terms of the series and adding those together. So the first partial sum would just look at the first term. The second partial sum would add up the first 2 terms. The 10th partial sum would add up the first 10 terms. So nth partial sum means it adds up the first n terms. Then we're going to do something special with this. So we start with an infinite series, we're looking at its partial sums, and we're going to make a sequence out of those values. So this can be a little confusing because we have a sequence within a series situation going on, but let's go through it. So we're taking the sequence of the partial sums, and writing this out, it would look like s sub 1, s sub 2, s sub 3, etc., listing them all out. And again, s sub 1 is just the sum of the first term, s sub 2 is the sum of the first 2 terms, s sub 3 is the partial sum of the first 3 terms, etc., all the way up until s sub n, which is all of the terms up to n added together. Then, this is where our understanding of sequences and their convergence comes in handy. So rather than trying to determine this series and all of these things added together, we're just going to look at this sequence of its partial sums and see if that sequence converges, since determining if a sequence converges is something we now know how to do. So the formal proof for this requires quite a bit of math, but I just want to focus on some examples to show you kind of how this works and what it looks like. We will also revisit this idea in my next video where we talk about the geometric series, so if you aren't feeling totally confident at the end of this video, don't worry, we keep talking about it in the next video. Alright, so for some examples, let's determine if the sequences of partial sums of the following infinite series converge or diverge. And I'm going to look at series that look familiar to some sequences we've already considered. So let's look at the sum of n equals 1 to infinity of 1 over n. This is the harmonic series. And then let's also look at the sum from n equals 1 to infinity of n. This is an example of an arithmetic series. So starting with the harmonic series, we can write out some of the terms. We have 1 over 1 plus 1 over 2 plus 1 over 3, etc. forever and ever, with the denominator just increasing by 1 each time. Then for the arithmetic series, we're just adding n equals 1, n equals 2, n equals 3, etc. So I want to focus on the harmonic series first, and then we'll come back to the arithmetic series after we've talked about the harmonic series. So let's look at the sequence of partial sums. So the first partial sum is just the first term, 1 over 1, that's 1. The second term is 1 over 1 plus 1 over 2, which is 3 over 2. Then the third partial sum is 1 over 1 plus 1 over 2 plus 1 over 3. So using some common denominators on fractions here, I'm getting 11 over 6. Then I'll just go ahead and compute these next two separately, just so you can see what it looks like. We have s sub 4, that's the fourth partial sum, is going to be 25 over 12. And then the fifth partial sum is going to be 137 over 60. And then the nth partial sum is just going to be the sum from I equals 1 to n of 1 over I. That's not super useful to us, I'm just writing it so we can get used to what it looks like. Okay, so it's hard to see what's happening to these values over time. Let's write them as decimals so maybe they look like something more understandable. So I have 1, 1.5, 1.83, 2.08, and 2.28. Remember, we want to know if this sequence converges. So we're looking at these values and we want to know if they converge. Does the limit as n approaches infinity of the nth partial sums exist? Just looking at the values, I don't really think it is approaching a certain value. But just me thinking that isn't really enough for it to be completely true. So we're going to look at a graph in a moment to see that it doesn't converge. It turns out that the harmonic series and whether it converges is a pretty interesting problem in mathematics, and it's not something I want to go completely into detail about here, but it's something to know about and to realize that it doesn't converge, which is really interesting. Alright, so here is the graph of the partial sums of the harmonic series, and we're using n from 1 up to 99. So this graph shows both the partial sums of the series and the sequence. So the sequence is just 1 over n, we've already talked about this, it converges to 0. But the partial sums seem to grow and grow and grow. So as n continues to approach infinity, the output, or the value of the partial sum, is also continuing to grow. It's growing quite slowly, but it's still growing. We're not settling on a specific value or approaching something in particular, like we are with 1 over n and the sequence of those values. So our conclusion is that the partial sums of the harmonic series are divergent. Alright, let's look at the sum from n equals 1 to infinity of n, our example of an arithmetic series, next. So this series is just 1 plus 2 plus 3 plus 4, on and on and on forever. So we're basically just adding the counting numbers together, 1, 2, 3, 4, 5, 6, etc. Just looking at this, I'm quite confident this sum is going to diverge. We're just adding numbers that get bigger and bigger and bigger together, so we keep adding bigger numbers, we're going to keep getting a bigger value. So I'm quite confident this series diverges, but let's just make sure the math works in the way that we've talked about. Specifically, let's look at the sequence of partial sums S sub n. The first partial sum is just 1. The second partial sum is 1 plus 2, which is 3. Then the third partial sum, we add 1 plus 2 plus 3, which is 6. Then the fourth partial sum, we add 1 plus 2 plus 3 plus 4, that's 10. And the fifth partial sum, we do 1 plus 2 plus 3 plus 4 plus 5, which is 15, and so on. So the nth partial sum is the sum from I equals 1 to n of I. So writing out this sequence of partial sums, I get 1, 3, 6, 10, 15, etc. And this sequence diverges. The numbers are growing and growing and growing. They're not approaching some certain value or slowing down in any way. We're just continuing to add numbers that get bigger and bigger. So we say that the partial sums of the arithmetic series, n equals 1 to infinity of n, diverge. So from these two cases, these two examples we've talked about, I want to make a conclusion. So since the sequence of partial sums of the sum from n equals 1 to infinity of 1 over n and the sum from n equals 1 to infinity of n diverge, we can conclude that the infinite series themselves also diverge. So since we've looked at the partial sums, and over time those partial sums don't approach any value, the overall series isn't going to approach any value. So if we add n terms together and we're not approaching anything, adding an infinite number of terms isn't going to suddenly make it converge in some way. Basically, if you take 200 things and add them together and they're not converging in any way, adding 201 isn't going to suddenly make it converge. So we can test by adding n things together and make the conclusion that adding an infinite number of things together has the same property. So if the partial sums diverge, then the infinite series diverges. We are going to make some similar conclusions for convergence. These two cases we looked at both diverged, but in the next video I'll show you a case where we have something that converges, but for now I just want to give you the formal rules so you have them for yourself. We say that an infinite series, which is the sum from n equals 1 to infinity of a sub n, converges if the sequence of its partial sums, s sub n, converges. So if we can add up n items and that is convergent, then we can conclude that adding an infinite number also converges. So writing this out a different way, if the limit as n approaches infinity of s sub n, of the partial sums, exists, then the series itself converges. And just as a reminder, for any n, the nth partial sum is equal to the sum from I equals 1 to n of a sub n. It's just the sum of the first n terms. Now, we have an additional conclusion that we're going to make, and it's that if the limit as n approaches infinity of s sub n is equal to some value s, then the infinite sum is equal to s. This means that if we found the sequence of partial sums to converge, we can conclude that the series is equal to that value at which it converges. Another way to say this would be if we add up the first n terms and we see that they are approaching a certain value, then we can conclude that the infinite sum also approaches this value. Okay, so these are the conditions for convergence. I just want to mention too, the opposite of converging is diverging. So if a sequence doesn't converge, it diverges. So this means that if the sequence of partial sums diverges, s sub n, then the infinite sum also diverges. Okay, that is it for this video. In the next video, I will introduce a geometric series and talk about how it converges and show it using the same ideas in this video. So check out that video if you're wanting a follow-up on these concepts. Thanks so much for watching, and I will talk to you in the next one.